If you think stars are too far apart to ever crash into one another, you're about to discover something strange. Stars can collide, and some of the most violent objects in the universe are created when they do. But here's the twist. When we imagine a stellar collision, we picture two enormous glowing balls smashing together like cosmic wrecking balls. That's not usually what happens. Sometimes, stars slowly spiral together. Sometimes one steals material from another. And in the most extreme cases, two dead stars, each containing more mass than the sun packed into a sphere only a few tens of kilometers across, can spiral inward until there is simply nowhere left to go. And when that happens, the universe can literally ring. So, can stars really collide? Yes, but the reason they collide is far more fascinating than the collision itself. First, we need to understand just how enormous the distances between stars actually are. Our sun may look enormous from Earth, but compared with the distance between stars, it is basically a tiny island in an almost unimaginably empty ocean. The nearest star system to our sun, Alpha Centauri, is more than 4 light-years away. That means a random head-on collision between two ordinary stars is extraordinarily unlikely. So if space is this empty, how do stars ever crash? Gravity. Stars don't usually wander randomly into one another. Instead, collisions and mergers are much more likely in crowded stellar environments, such as globular clusters, where huge numbers of stars are packed into relatively small regions. And there's another important route to a stellar collision: binary stars. Binary stars are two stars gravitationally bound together, orbiting a common center of mass. They can spend millions or billions of years circling each other. But eventually, things can get complicated. One star can expand as it ages and begin transferring material to its companion. The two stars can lose orbital energy, move closer together, and in some cases merge into one object. And here's where things get controversial. For decades, astronomers have debated how some bizarre-looking stars known as blue stragglers are created. These stars appear younger, hotter, and more massive than the other stars around them, even though they formed in the same ancient stellar environment. One possible explanation has been stellar collisions. Another is mass transfer between binary stars. And recent observations have strengthened the case that binary interactions may be more important than simple star-on-star collisions in many environments. A 2026 ESA/Hubble study found strong links between blue stragglers and binary systems, particularly in less crowded stellar environments. So the idea that every young-looking star is the product of two stars smashing together would be misleading. But actual stellar mergers absolutely do happen, and we have observed evidence for them. One remarkable example is V1309 Scorpii, an object whose behavior has been interpreted as the aftermath of two stars merging. The stars had been in an extremely close binary system before the dramatic outburst. Eventually, the system underwent a stellar merger. But ordinary stars aren't the only stars capable of colliding. Now we enter a much more extreme world. Imagine taking something roughly the size of a city and giving it a mass comparable to the sun. That is a neutron star. A neutron star is the crushed remnant left behind after certain massive stars explode. It can contain an enormous amount of matter compressed into an incredibly small volume. Now imagine two neutron stars orbiting each other. At first, their orbit can take an incredibly long time to shrink. But there is a problem for them. They emit gravitational waves. These are not ordinary waves moving through space, like sound waves through air. They are ripples in space-time itself. As the neutron stars lose energy through gravitational radiation, their orbit gradually shrinks. They move closer, then faster, then closer still. Eventually, the process accelerates dramatically, and in the final moments, the two objects can orbit each other hundreds of times per second. Then, they merge. We know this isn't just theoretical. On August 17, 2017, scientists detected an event called GW 170817. It was the first gravitational wave event observed from two merging neutron stars, and telescopes also detected light from the same cosmic explosion. The event occurred in a galaxy roughly 130 million light-years away. Think about that. The collision happened about 130 million years ago. Dinosaurs had not yet appeared on Earth. Human beings didn't exist. And the ripples from that ancient event finally reached our planet in 2017. But the gravitational waves weren't the only thing astronomers detected. The merger produced a powerful burst of gamma rays and an explosion called a kilonova. And this is where stellar collisions become more than spectacular cosmic violence. They can become cosmic factories. During neutron-star mergers, extremely neutron-rich material can be thrown into space. Under those extraordinary conditions, heavy elements can form through rapid neutron capture. That process is associated with the production of some of the universe's heaviest elements, including precious metals such as gold and platinum. So when you look at a piece of gold on Earth, you're looking at something with a truly ancient cosmic history. The atoms didn't originate here. Some of the heavy elements in our universe were forged in extreme cosmic environments, including neutron-star mergers. But wait, there is another surprising possibility. What happens when a neutron star collides with a black hole? That can happen too. And unlike two ordinary stars gently merging into a larger star, a neutron star black hole encounter can end with the neutron star being violently torn apart, or, depending on the masses and spins involved, swallowed with little visible debris. That's important because not every cosmic collision produces a bright fireworks display. Sometimes the most dramatic event can be almost invisible in ordinary light. And here's the part that sounds like science fiction, but isn't. Scientists don't necessarily need to see a collision directly. They can detect its gravitational waves. LIGO and other gravitational wave observatories can measure incredibly tiny distortions caused by massive objects spiraling together. It's almost like listening to the universe rather than looking at it. And that's revolutionizing astronomy. Before gravitational wave astronomy, scientists primarily studied the universe using electromagnetic radiation, visible light, radio waves, X-rays, gamma rays, and infrared radiation. Now, they can also study violent cosmic events through the ripples they send through space-time. It's a completely different way of observing the cosmos. But let's return to the original question. Can stars collide? Absolutely. Ordinary stars can merge. Binary stars can spiral together. Dense stellar clusters can increase the chances of close encounters. And dead stars, such as neutron stars, can undergo some of the most violent mergers known. But here's the misconception worth remembering. The universe isn't filled with stars constantly crashing into each other. Space is overwhelmingly empty. Most stars will never experience a direct collision. Instead, gravity slowly shapes their relationships over enormous stretches of time. And sometimes, after millions or billions of years, those gravitational relationships end in a merger. The result can be a new star, a spectacular outburst, a kilonova, a black hole, or a gravitational wave signal traveling across the universe. So perhaps the most incredible thing about stellar collisions isn't that stars can crash. It's that the universe can wait billions of years for two objects to find their final dance, and then turn that final moment into a message that crosses millions of light years before reaching us. If you enjoy uncovering the strange but scientifically proven mysteries of the universe, follow for more. Because the next cosmic mystery might be even more surprising.